I didn't have the courage like these other students, and so I'm still working on building up the courage. Subsequence of sigma with the same relative order as that of pi. And otherwise, sigma is said to avoid pi. So let's see an example. So let's look at this 7 permutation. And this means that the number 1 maps to 7, 2 maps to 2, 3 maps to 6, 4 maps to 5, 5 maps to 3, 6 maps to 1, and 7 maps to 4. And this 7 permutation contains the permutation 4, 3, 1, 2. And it's because this subsequence, 7, 5, 1, 4, has the same relative order as 4, 3, 1, 2. So the number 7 is the largest of this subsequence, similar to 4 here. 5 is the second largest, similar to 3 is the second largest. 1 is the smallest here and here. And 4 is the second smallest, and 2 is the second smallest here. So this 7 permutation contains 4, 3, 1, 2, but avoids 1, 2, 3, 4. And this is equivalent to saying that there's no increasing subsequence of length 4, and you can check this. Okay? So a basic question you may want to look at, and people have been studying for a very long time, is Sn pi, the number of n permutations avoiding pi. So the number of n permutations is n factorial, and you would expect there to be somewhat smaller number of permutations that avoid a given permutation, pi. And we'd like to understand what these numbers are. There are classical results in this area of McMahon and Knuth, which says that this Sn pi, for pi being any 3 permutations, so it doesn't matter which of the 6 3 permutations you pick, it's always the nth Catalan number. And you may ask what happens now for 4 permutations, 5 permutations. Now, the nth Catalan number, this is very roughly 4 to the n. Let's forget about lower order terms. So this grows exponentially in n with constant 4. Does this happen in general? And this is the famous Stanley-Wilf conjecture from 1980. It says for each permutation pi, there is a L of pi, this is called the Stanley-Wilf limit of pi, such that Sn pi to the 1 over n tends to L of pi. So this means that Sn pi grows exponentially with exponential constant L of pi. This problem is equivalent to a seemingly weaker conjecture that it just grows at most some constant to the n. And the reason for this is that Sn pi is super multiplicative. So Sn plus m pi is greater than or equal to Sn pi times Sm pi, and this is easy to show. You can assume by symmetry that pi, its first element's larger than its last element, and then you can take an n permutation that avoids pi and an m permutation that avoids pi. You can concatenate them, making all the elements of the m permutation bigger than all the elements of the n permutation, and you'll get an n plus m permutation which also avoids pi. Okay, so in addition to wanting to prove this, well, what they actually wanted to prove originally, Stanley thought that L of pi should always be k minus 1 squared if pi is a k permutation. And Wilf independently was studying this and thought it should always be at most k plus 1. Now these obviously contradict each other. And so they came, and it's not difficult to show that they're both false. So they came to this weaker conjecture that this limit should always exist. Now, about that time, there was a result of Regev, which implied that for the identity permutation, this Stanley-Wilf limit is k minus 1 squared. And this follows from this RSK algorithm. Okay. Now, the first progress, or huge progress on this problem, was made by Noga and Friedgut. They proved that Sn pi is at most some constant in pi to the n times gamma of n. Now, what is this gamma of n? So if this gamma of n was a constant, that would be the Stanley-Wilf conjecture. But it grows very slowly to infinity. In fact, it grows much slower than the inverse Ackermann function. So it's the number of times you need to iterate the inverse Ackermann function to get down to 1. I've never seen something so slowly growing naturally appear in some proof. It gets as close as you possibly can without proving it. It's the second formula in the poster for this conference. So it's a great result. And then the next big breakthrough was by Adam Marcus and Gabor Tardos, where they proved the Stanley-Wilf conjecture. So they proved that for each k permutation pi, the Stanley-Wilf limit of pi exists and satisfies that it's at most something that looks roughly like double exponential in k. So starting with the Stanley and Wilf, the very natural question here was, what is L of pi? And for a k permutation. And in particular, how large can it be for a k permutation pi? This would seem to be a central question in the area. Now, there's been a lot of work in this area. There's a couple of books written on combinatorics of permutation now, many papers and surveys. There's even an annual conference that's been going on for more than a decade in this area. And there was a conjecture that L of pi should always be at most k minus 1 squared for a k permutation pi. Basically, the identity permutation is roughly the worst. This is saying it's essentially the worst possible, and I mean, it's the easiest one to avoid in some sense. And he offered a cash prize in the spirit of Erdős for this problem. It took 7 years, but it was eventually disproved. So it's off by about 5% at least.
Each one got $20 in this case?
I don't know how they split it. It's a good question. Maybe not. Well, maybe it's not a good question, but it's only $20. Okay, so it's conjectured to be at most 9. So this is not true, but the revised conjecture was that the Stanley-Wilf limit should always be on the order of quadratic in k, for every k permutation pi. And there were much stronger conjectures which implied this. And so it's not difficult to show that it's at least quadratic in k for every k permutation. But proving it, it's at most, well, that was an open problem. There were huge tables constructed for Sn pi. And they all seem to suggest that this should be true. In addition, there was a lot of heuristic arguments that were given that why this should be true. And in the various surveys, they say this is a widely believed conjecture, even from a couple years ago. So the first main result I want to tell you about is that this is very false. So almost all k permutations pi satisfy that the Stanley-Wilf limit is at least exponential in root k. And so I'll show you the proof of that shortly. So this is a question about permutations, and it really fell in this area of enumerative combinatorics, which is quite popular. It turns out to really approach this problem, it seems that techniques from extremal and probabilistic combinatorics, where Noga is an expert and has led the field for many years now, you need to use these tools. So all matrices we consider are binary, so that means entries are 0 and 1. And the mass of a matrix is the number of 1 entries. That's the sum of the entries. Now we need a notion of matrix containment. So a matrix A contains another matrix P if from A we can obtain P by deleting some rows and columns and changing some entries from 1 to 0. So this is very similar to graph containment and looking at the adjacency matrix. What we're doing here is you can view a matrix P as a bipartite graph. The rows form one part, the columns form another part, and if you have a 1 in a given entry, it means that row and column are adjacent. And that gives you an ordered bipartite graph. The rows are ordered, the columns are ordered. This containment relation is saying that A contains P as a matrix means that this bipartite ordered graph associated to A contains the bipartite ordered graph corresponding to P. It's the same thing. And we have this classical extremal number, NP. It's the maximum mass of an n by n matrix which avoids P. And in general, this is a very hard problem to estimate, this extremal number. How many 1 entries can you have so that in an n by n matrix so that it avoids P? In particular, if P is the all ones k by k matrix, this is the famous problem of Zerenkewicz, which is still quite open. Noga and others made some nice progress on this problem. Now, in the case of permutation matrices, well, P will associate the permutation pi, so we'll write extremal number of n pi to be the extremal number of np. So how many, so P will be the permutation matrix for pi, and we'll often confuse permutations with their corresponding matrix. So this is another well-known conjecture in this area of Zoltan Ferretti and Peter Heinel. And they conjectured if you have a permutation pi, this extremal number, n pi, is only linear in n. You can only fill it with a linear number of ones in the n by n matrix. Otherwise, you'll have to get a copy of pi. This is equivalent to the existence of the Ferretti-Heinel constant, C of pi. This is the limit of this extremal number divided by n. And the reason that this is equivalent is very much the same as why the Stanley-Wilf limit is equivalent, is that this extremal number is super additive. And this is a simple exercise similar to the proof that we saw there. Yes?
What is the definition of sum? I might have missed that. So changing sum and
Arbitrarily. I mean, so you can do as whichever entries you want. So you're basically looking at a sum matrix of A. You take some of the rows and the columns, and then as long as there's ones in certain positions, the ones that are in the positions of P, then you have this containment. Is that okay? Okay. Right. Okay, so what is the relationship between this Ferretti-Heinel conjecture and the Stanley-Wilf conjecture? Well, Clauser had this nice proof that the Stanley-Wilf conjecture would follow from the Ferretti-Heinel conjecture, and in particular, the Stanley-Wilf limit's at most exponential in the Ferretti-Heinel constant. So this constant's at most exponential, and what Adam Marcus and Gabor Tardos proved was that the Ferretti-Heinel conjecture holds, and the C of pi is at most this expression, and therefore the Stanley-Wilf conjecture holds. And if we have time, we'll show proofs of everything, almost everything. Now, there's a better dependence that was discovered a few years ago by Cebulka. For every permutation pi, he shows that the Stanley-Wilf limit and the Ferretti-Heinel limit are polynomially related. And this first bound is best possible for some pi. For example, if pi is the identity permutation, the Stanley-Wilf limit we saw was, if it's the k permutation, is k minus 1 squared, and the C of pi will be on the order of k. And then this bound is not tight. We can improve it from 4.5 to 3, and I don't think that's even best possible. These proofs take a number of pages. The methods we have shorten them a lot. This is now a few lines, and we'll hopefully show that soon. So what follows from this nice result of Cebulka is that the Stanley-Wilf limit is at most exponential in k log k, and we can get rid of the log k, again by these new methods. It's somewhat new in terms of they haven't been properly defined before, but it's also implicit in previous works. And so it's sometimes very helpful to really define something and start working with it. And it's this notion of interval minors. So so we need a notion of contraction. So for those familiar with graph minors, there's a notion of contraction there where you have two adjacent vertices, and you would replace those two vertices by one vertex whose neighborhood is the union of the neighborhoods of those two vertices. For interval minors, we have a matrix, and we contract two consecutive rows or two consecutive columns. And so instead of this notion of adjacency, we are contracting with consecutive here. So what is this? So if you have two consecutive rows of a matrix, we replace the two rows by a single row with a 1 in an entry of the new row if at least one of the two entries in the original two rows is a 1. Contraction of columns is defined similarly. So this is just an example here. Here's a matrix with 3 rows, 4 columns. Let's see what happens if we contract the first 2 rows. So we replace these 2 rows by a single row, and as long as there's a 1 in at least one of the 2 entries, we get a 1 in the corresponding entry. So in the first 3 columns, the first 2 rows have at least 1 1 in them, but the last one it's a 0. And so that new row you're going to construct from the old 2 here would be 1 1 1 0. Okay? So this is this notion of contraction, and then you can ask a similar extremal problem, and you can define a notion of minors here. So matrix P is an interval minor of A if P is contained in a matrix obtained from A by contraction of consecutive rows and columns. So you're allowed to contract rows and columns, and then it would be the usual containment once you've done all these contractions. Okay, so why is this an interesting notion? Well, one thing that's very interesting, they're very different notions than the usual containment, but if P is a permutation matrix, you can check that it's equivalent. So interval minor is equivalent to the usual containment order for permutation matrices, if P is a permutation matrix. Okay. So we're going to let the all ones K by K matrix be denoted by JK. And you can notice that it contains all K permutations, right? We have 1s in the corresponding spot because everything's a 1. Of course, the converse is false, but we'd like something in the other direction. Now, the usual containment doesn't work, but what you can show is that there exists a K-squared permutation, and K-squared's tight here. This is a simple lemma whose matrix contains JK as an interval minor. So there's going to be a permutation matrix in terms of containment, in terms of interval containment, you have JK as an interval minor. This K-squared here is tight. What do such matrices look like, or permutations? Well, these are Sudoku permutations. So if you've ever played Sudoku, you want to fill up a 9 by 9 square so that every row has the numbers 1 through 9. Every column has the numbers, every row has the numbers 1 through 9. Every column has the numbers 1 through 9. And each of these blocks, these 9 blocks, should have the numbers 1 through 9. And of course, there's a way of filling this in. A Sudoku permutation would be just take one of the 9 numbers, and you'll have a 1 in every row, column, and block. And these will be precisely the Sudoku permutations which have this property. And in addition to it working for 9 by 9, it also works for K squared by K squared, and this is a simple exercise. You read the newspaper and you open up to Sudoku, and at least in the States, it says this is not math. They're trying to make it more appealing to people. But Sudoku is math. I mean, it really, maybe we're tricking people into doing mathematics. But you can define explicitly an example permutation pi. So if pi is of the form, if you have a number of the form ak plus b plus 1, where a and b range from 0 to k minus 1, you can switch a and b. And this you can check quite easily as a Sudoku permutation. Okay. So with this lemma, this will be a helpful lemma. We'll look at the extremal problem for interval minors. So for a matrix P, let Mn of P be the maximum mass of an n by n matrix which does not contain P as an interval minor. Okay, so this is equivalent to this extremal number when P is a permutation matrix. But if P is an all ones matrix, this will turn out to be much smaller, this N of P. What we show is that Mn of Jk for the all ones matrix is bounded from below and above by something that's exponential in k times n. So it's a linear bound in n, and the constant dependency in k is exponential. And I'm not careful about these constants here. So what does this say? What is this question asking for? You have an n by n matrix. How many ways can you fill in ones so that no matter how you partition the rows into k intervals and the columns into k intervals, you will always have one of the k squared blocks will be all zeros. So here's k is 3, and I partition, no matter how I partition the rows into k intervals, so 3 intervals here, and the columns into 3 intervals, this is equivalent to saying that no matter how I do that, one of these k squared blocks will all be zeros. Everything in here will be a 0. For no matter what no matter what partition we get, we'll have one of these blocks always be a 0. Okay. So we'll do the lower bound, and then we'll show that that implies these new lower bounds on the Stanley-Wilf limits and Faraday-Heine limits. So how does that work? So to prove that result, we're going to find one n by n matrix, and n here is going to be 2 to the r. K will be 20 times r, so linear in r. We're going to find this n by n matrix, M, which has mass n to the 3 halves. So there's going to be a lot of ones in this n by n matrix we're going to construct. In fact, you can play around with the parameters here, and you can make this not only be n to the 3 halves, you can make it 1 minus epsilon times n squared. You're giving up a little bit on the k value, but you can make it almost complete, and it's going to avoid jk as an interval minor. So you're going to fill in this exponentially large in k n by n matrix, and you can fill it up a lot, and still you can avoid jk as an interval minor, which is kind of counterintuitive. Okay, so we'll prove that shortly. And as a corollary, we get that mnjk is going to be at least exponential in k times n. The way we do that, so we found just one matrix here, but this mnjk, because this is a power bigger than 1, 3 halves, we'd like to say that mnjk is superadditive. We don't know in general if that's true, but it's close to being superadditive. So if you put together a bunch of these matrices which avoid jk minus 1, then in the natural way, you'll avoid jk. And so it's close to being superadditive, and then you get this type of bound from that. And then as a corollary from this, we get that there's a k permutation pi whose Faraday-Heine constant's exponential in root k. So if this was a Sudoku permutation, we'd get this, because that k permutation pi would avoid as an interval minor j sub square root of k, and then we would be able to get this out of there. And if you take a random permutation, you can get a little bit worse bounds just by applying this. And if you're a little bit more careful, you can get rid of the little bit worse part. And so it follows from here, because we know the Stanley-Wilf limit and the Faraday-Heine limit are polynomially related, that we get that it's going to be at least exponential in root k. Okay. Okay, so I gave this talk, an early version of this talk at the IES, and Noga was there, and at the end of the talk, there was some part of the proof, of course, that Noga optimized. At the end, he very politely came up after my talk and showed me how some part of it could be done a little bit nicer. And it got me thinking for a while, and I kept thinking, and eventually I optimized it a little bit more. So Noga will, hopefully this will look a little bit different toward the end of the proof. So here's okay. So how are we going to make this counterintuitive matrix M, which has a lot of one entries, and yet still avoids JK as an interval minor? So a natural thing to do, being a disciple I was Benny Sudakov's student, which was Noga's student, and we all have been very much impressed by the whole area of the probabilistic method. And so the natural thing to do here is to define a random matrix M. And the natural thing to do would be you would flip a coin for each entry. That doesn't work here. So for each entry, you would flip a coin independently of the other entries normally. So you have to do some other type of random matrix here. And so we have to define that. So a dyadic interval is of the form, so it's between a multiple of a power of 2 and the next multiple of a power of 2, of that power of 2. So it's between two consecutive multiples of a power of 2. So that's what a dyadic interval is. A dyadic rectangle is a product of two dyadic intervals. We're going to let Q be some constant depending on R, and it'll be, this is so that the bounds will work later. And we're going to take a random family of dyadic rectangles, R, which is contained in n by n. So there's all these dyadic rectangles, and each one of them we're going to include in this family R independently with probability Q. So we're taking a random family. There's all these dyadic rectangles. We're just going to take each one with probability Q. And then an entry of M is 1 if and only if it is not in any rectangle in R. So we have this family of dyadic rectangles. For each rectangle, we're going to get that rectangle's all zeros if it's in R. And so otherwise, if none of those rectangles contain a particular entry, it's going to be a 1. So let's see an example of this. If we have 3 rectangles, so this column here is a dyadic rectangle, this is another dyadic rectangle, and this 2 by 2 here is a dyadic rectangle, then we would get that this matrix would be, if that was our family, this would be the resulting matrix we'd get out of it. Okay. So there's 2 parts to this proof. The first is to look at how big we'd expect the mass of this matrix to be. So how many 1 entries will there be? So there's a very simple way to compute the expected mass of this matrix. Notice that if you have the numbers 1 through n, and n is 2 to the r, for each element between 1 and n, there's exactly r plus 1 dyadic intervals that contain it, 1 for each power of 2. So each entry of this matrix is in exactly r plus 1 squared rectangles, dyadic rectangles. And so the probability that each of these rectangles is missing is 1 minus q to the r plus 1 squared. So by linearity of expectation, the expected mass of M is going to be this 1 minus q to the r plus 1 squared times the number of 1 entries, which is the number of entries, which is n squared. And when you put those values in, you get n to the 3/2 here. So that's the expected mass. Now we're going to look at, we're going to look at the probability that this matrix, this random matrix M, avoids JK as an interval minor. So if you can show it's very unlikely that M will contain JK as an interval minor, and the expected mass of M is large, then you can put those together and show there exists a matrix M which has large mass and avoids JK as an interval minor. Okay, so here's the new part. So what would happen if M contains JK as an interval minor? Well, then there are partitions of the rows into k intervals, and a partition of the columns into k intervals, such that for every one of the k squared rectangles you get, these submatrices, they're going to be not all zeros. So I have these intervals of rows and these interval of columns. This is my n by n matrix. And each of these rectangles, so here's IA and LB, and that rectangle, and probably you can't see any of this, but I'm telling you that rectangle, for every single one of these k-squared rectangles, there's going to be at least one entry in it. Okay. So let UA and VB be the smallest dyadic intervals with IA in UA and LB in VB. So we're going to look for each of these intervals, what's the smallest dyadic interval that contains it? Now, here's a simple claim. These dyadic intervals are unique. So U1 to UK, these are all unique, and V1 to V are distinct, and V1 to VK are distinct. Why is that? Well, suppose there was a UI and a UI prime. There was a... Whoops. Oh, we went the wrong direction. Okay. Sorry. Okay, right. So we're trying to show that these U1s to UK are distinct. Suppose I have an interval I sub A and I sub A prime. And they happen to have the same dyadic interval, which is the smallest that contains both of them. So UA is equal to UA prime. So that means the smallest dyadic interval that contains them, that contains either one of them, is the same. Then, because these are disjoint intervals, one of the two has to be in the left half or the right half of this dyadic interval, and therefore it has to be in a smaller dyadic interval, which is just that half. So these intervals are distinct. Okay. Now, if U and V are dyadic intervals, with Ui contained in U and Vj contained in V, then that rectangle, that dyadic rectangle, U times V, can't be in R. Why can't it be in R? Well, suppose it was in R. Then the matrix M in the U times V matrix, it's going to be all zeros. Now, these are contained in here, so Ui times Vj will also be all zeros, and therefore I sub I and L sub j, that matrix, that subrectangle will be all zeros as well. That's also contained. And they're not supposed to be that way. So we're going to have all of these missing dyadic rectangles inside of, so they're not in R. Now we come to some more enumerative question, which is not so difficult to bound. Let U be a subset U1 to UK. So we're going to look now, instead of looking at all these partitions into intervals, we're going to look at the U's that we get from this. And so suppose we have a subset U, and we get a U1 to UK. That's what U is made of. We're going to let X of U be the number of dyadic intervals U for which there exists an I, with UI being a subset of U. So we have these K dyadic intervals, U1 to UK, and you can think of this as being 1 to n. At the top of this complete binary tree, here we have the first n over 2 integers, so we have n over 2, and we split it in half into 2 smaller dyadic intervals, and you keep splitting down here. So X of U is, we have K u1 to uk here, we have these k intervals, and x of u would be counting the number of vertices of this complete binary tree that are above at least one of them. So here in this example, if these were 4 of these dyadic intervals, we would get 5. We get x of u would be 5 in that example. Okay. So we're going to let fxk be the number of u with x of u equal to x. So how many of the possible k vertices of this complete binary tree can you get where their upset in this complete binary tree has size exactly x? This is fxk. And you can try bounding fxk from above, so this will be helpful. Here's a little exercise. You can prove fxk is at most some function in x and k. It's a simple exercise. This bound will be sufficient for us. I asked Yufei Zhao, my student, who was trained properly in enumerative combinatorics, and he gave me a nice formula for fxk. So there's a formula that you can use. It's a simple sum, so you can get a more precise answer here. But we want to bound this probability that we get at jk as an interval minor, and so we can bound it above by, once we fix u and the set v, we get a probability 1 minus q to the xy, where x will be x of u and y will be x of v. This is the number of rectangles that needs to be missing because of this fact here. So we're going to get a probability 1 minus q to the xy at most that all of those rectangles are missing, those particular ones. And then we get the number of choices here. So we get fxk times fyk, possible choices for what these sets u and v could be. So we want to bound this sum. Now we have some upper bound on fxk, and you can just substitute that in. And you have this sum over x and y being at least k. And you can see that it rapidly decays, at least exponentially. So the main term here is when x and y are equal to k, and then you can bound it from above by twice that. And 1 minus q is at most e to the minus q, so you can just bound it by that first term. And you substitute in, and you get that this is at most n to the minus 20. So it's very unlikely that jk is an interval minor of this matrix M. Okay, so it's now a very simple exercise to put the fact that, so if you don't immediately see how to do it, just read the first few chapters of the probabilistic method. In fact, the first 1 or 2 will be sufficient. And you will be able to put these two facts together to show that there exists a matrix M with a lot of 1s that has no jk as an interval minor. Is there any questions here? Yes, Yuval.
So the lower bound, you have a lower bound for the expectation of the mass, what would end in the 3 halves?
It's an equality for the expected value. I mean, it was 1 minus q, to this power r plus 1 squared, because you know exactly the probability that a particular entry, yes?
So but you also have, just the expectation is not enough. You also do a second moment, or how do you?
Great question. This probability is really small. It's at most n to the minus 20. And it's always the mass is always at most n squared. So you can put that together to say that so you can either use Markov's, or the very clever way that Noga did it was by combining some expected value was greater than 0, and you interpret from that that something exists that has the property you're looking for. So linearity of expectation.
Initially you said this probability is small, but you need it to be very small.
You need it to be very small, but you get that from this estimate. Yes, thanks. Okay, so if you're asleep now or weren't following any of this, this is the hard part. Now let's do the easy part. So there's simple, quick bounds. So we're going to use these interval minor concept to get some quick results that I think are really nice. So these interval minors, they appeared before implicitly, but not explicitly. And when you use this language, things become much cleaner and simpler. So we were looking at lower bounds here. What happens with upper bounds? So we're going to let Tn pi be the number of n by n matrices which avoid pi. Now here's a nice result of Clauser. It's simple lemma. Tn pi is at least exponential in this extremal number, the number of ones you can fill an n by n matrix without having pi. And it's at most some other exponential in this extremal number. So the lower bound's very simple. If you have these one entries in some matrix that avoids pi, well, you could switch them to 0. So you have two choices for each of these entries, and you have at least 2 to the extremal number of n pi choices. The upper bound is a little bit more clever using this interval minor idea. So it follows by induction from a nice inequality here. T2n pi is at most Tn pi times 15 to the extremal number of n pi. And how do you prove this inequality? Well, let's look at a 2n by 2n matrix which avoids pi. And let's partition the rows into pairs and the columns into pairs, and let's contract. So we started off with a 2n by 2n matrix, and we got an n by n matrix from this. So each of these 2 by 2 squares became a single entry. If it was all zeros, you'd get a 0, but if there's at least one 1, you get a 1 in the corresponding entry. So let's bound the number of choices for this 2n by 2n matrix by using the n by n matrices. So how many possible images are there? Well, when we do these contractions, we're also going to avoid pi. So there's at most Tn pi possible choices for this image. And how many ways, given the image, is there to get the original matrix? Well, for each 0, that has to be all zeros. For each 1, which there's at most in the extremal number of n pi of those, you have 15 choices. You have to fill a 2 by 2 matrix with 1s and 0s so that there's at least one 1. So you get 15 choices to the extremal number of n pi. Okay, so you get this nice result out of that. But Kibolka proved a much better bound, a quadratic upper bound, which is tight in some instances, we know. So we're going to prove a new inequality. Sn pi, the number of big N by big N permutation matrices that avoid pi, is at most the number of little n by little n matrices which avoid pi. They don't have to be permutation matrices, times t to the 2 times big N. And t is some parameter which we'll choose later. So big N is equal to t times little n. So how do we prove this? Well, it's the same proof idea. You split it up instead of 2 by 2, t by t. You do this contraction. So you start off with a Tn by Tn permutation matrix. You do this contraction. You get an n by n matrix, which also avoids pi. So there's Tn of pi choices for that. Now, this is a permutation matrix. So there's exactly one 1 in every row, in every column. When we do this contraction, we'll get at most k1s in each of these rows. So given the image, how many choices are there for the original matrix? Well, there's at most k1s in the first row. So let's look at the first row here and see how many possible places that first 1 could be, given what we know here. Well, the first 1 can only be where there's a 1 in that block. So there's at most k blocks here that have a 1, and each of those blocks in the first row have k entries. So you have at most k squared choices for where to put the first 1 in, the 1 in the first row. And that's true for every row. So for every row, there's going to be at most t squared places given this image for where to put the 1 in. And so therefore, there's going to be at most t to the 2 times big N. This is big N by big N choices for the pre-image. Is this clear? Okay, so we can just apply this inequality in the right way. So if you take t to be c of pi, the Faraday-Heinel constant, you'll be done. There's a slight issue with this. C of pi may not be an integer, and then you'll just round. But suppose it's an integer. Then you get out of this that Sn of pi is at most exponential in big N times c of pi to the 2n. And this comes from substituting in this bound here. And when you raise both sides to the 1 over big N and take the limit, you get this theorem of Kibolka, this nice result. Okay. I think I'm out of time here. Let me finish with some concluding remarks. So I was going to show you the nice proof, Marcus and Tardosh proof, the beautiful proof of the Stanley-Wolf conjecture, and using this interval minors, and using interval minors in a similar way, you can improve on the bounds. So that's the proof. I hope it was clear. Let me finish by saying this is a fun area of problems. The general belief originally was that things like that the identity permutation was the one that was the easiest one to avoid. And the small examples seem to suggest that, which it turns out to be false. And in fact, the opposite should be true. The reason why things should have large Stanley-Wolf limit is that they actually are more like random, and they contain small permutations, all of them. So a nice conjecture here is that if your permutation pi avoids a fixed permutation, then the Stanley-Wolf limit of pi should only be polynomial in K. And that's some way of characterizing when the Stanley-Wolf limit should be. It's not a perfect characterization, but it's some way of saying that when is the Stanley-Wolf limit small? So I want to finish by saying happy birthday to Noga. Hopefully he enjoyed the talk. He looks very happy here, and he looks somewhat happy here as well. And thank you.